Hello my dear students, welcome to Teacher at Home. Today class we are going to learn the chapter 9 Gravitation. We have learned about the motion of objects and force as the cause of motion. We have learned that a force is needed to change the speed or direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun, the moon goes around the earth. In all these cases, there must be some force acting on the objects, planets, and on the moon. Isaac Newton could grasp that the same force is responsible for all this. This force is called the gravitational force. In this chapter, we shall learn about the gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for the objects to float in liquids. Gravitation. We know that the moon goes around the sun, around the earth. An object, when thrown upwards, reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that it is the earth. If the earth can attract an apple, can it not attract the moon? Is the force the same in both the cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of the orbit, the moon falls towards the earth instead of going off in a straight line. So it must be attracted by the earth. But if we do not really see the moon falling towards the earth, let us try to understand the motion of the moon by recalling activity. Take a piece of thread, tie a small stone at one end, hold the other end of the thread and whirl it round. Note the motion of the stone. Release the thread. Again note the direction of motion of the stone. Before the thread is released, the stone moves in a circular path with a certain speed and change direction at every point. Change in direction involves change in velocity or acceleration. The force that causes this acceleration and keep the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center-seeking force. In the absence of this force, the stone flies off along a straight line. This straight line will be a tangent in a circular path, tangent to a circle. A straight line that meets the circle at one and only one point is called the tangent to the circle. Straight line ABC. It is a tangent to the circle at a point B. The motion of a moon around the earth is due to the centripetal force. Centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, apple does attract the earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. Mass of an apple is negligibly small compared to that of the earth. So we do not see the earth moving towards the apple. Extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all the objects in the universe attract each other. This force of attraction between objects is called the gravitational force. Universal law of gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of the masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. Let two objects A and B of masses m and small m lie at a distance d from each other as shown. Let the force of attraction between two objects be F. According to the universal law of gravitation, force between the two objects is directly proportional to the product of the masses, F proportional to m into m. and the force between the two objects, it is inversely proportional to the square of the distance between them. F proportional to 1 by d square. F proportional to m into m by d square. F is equal to g m into m by d square, where g is the constant of proportionality and is called the universal gravitational constant. By multiplying crossways, F into d square is equal to g capital M into small m. That is, g is equal to fd square by m into m. SI unit of g can be obtained by substituting the unit of force, distance and mass in equation as Newton meter square per kilogram square. The value of g was found out by Henry Cavendish by using a sensitive balance. Accepted value of g 6.673 into 10 to the power minus 11 Newton meter square per kilogram square. We know that there exists a force of attraction between any two objects. Compute the value of this force between you and your friend sitting close by. Conclude how you do not experience this force. This law, it is universal in the sense that it is applicable to all bodies, whether the bodies are big or small, whether they are celestial or terrestrial. Inverse square. Saying that F is inversely proportional to the square of D. This means, for example, that if D gets bigger by a factor of 6, F becomes 1 by 36 times smaller. Example, the mass of the earth is 6 into 10 to the power 24 kilogram and that of the moon is 7.4 into 10 to the power 22 kilogram. If the distance between the earth and the moon is 3.84 into 10 to the power 5 kilometer, calculate the force exerted by the earth on the moon. Given G is equal to 6.7 into 10 to the power minus 11 Newton meter square kilogram per kilogram square. The mass of the earth M is equal to 6 into 10 to the power 24 kilogram. Mass of the moon is 7.4 into 10 to the power 22 kilogram. The distance between the earth and the moon D is equal to 3.84 into 10 to the power 5 kilometer. So 3.84 into 10 to the power 5,000 meter. 3.84 into that 1000, it is being added here, 10 to the power 8 meter. G is equal to 6.7 into 10 to the power minus 11 Newton meter square kilogram per kilogram square. Force exerted by the earth F is equal to G M into M by D square. Applying all the values here, we get 2.02 into 10 to the power 10 to the power 20 Newton. Importance of universal law of gravitation. Universal law of gravitation successfully explained several phenomena which were believed to be unconnected. The force that binds us to the earth, the motion of the moon around the earth, the motion of planet around the earth, and the tides due to the moon and the sun. Free fall. Let us try to understand the meaning of free fall by performing the activity. Take a stone, throw it upwards, it reaches a certain height and then it starts falling down. We have learned that the earth attract an object towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of falling objects? While falling, there is no change in the direction or motion of the objects. But due to the earth's attraction, there will be a change in the magnitude or the velocity. Any change in velocity involves the acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth gravitational force. Therefore, this acceleration is called the acceleration due to gravitational force of earth and is denoted by g. Unit of g is same as that of the acceleration, that is meter per second. We know that the second law of motion, that force is the product of mass and acceleration. Let the mass of the stone activity is 9.2 bm. We already know that there is acceleration involved in falling objects due to the gravitational force and denoted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is F is equal to mg. mg is equal to g into m by d square. G is equal to gm by d square, where m is the mass of the earth and d is the distance between the object and the earth. Let an object be on or near the surface of the earth. The distance dA will be equal to r, the radius of the earth. Thus, for the objects on or near the surface of the earth, mg is equal to g into m by r square. G is equal to gm by r square. Earth is not a perfect square. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at poles than at the equator. For most calculation, we can take g to be more or less constant or near the earth. But for objects far from the earth, the acceleration due to gravitational force of earth is given by equation. To calculate the value of g. To calculate the value of g, we should put the values of g, m and r in equation, namely universal gravitational constant g is equal to 6.7 into 10 to the power minus 11 Newton meter square per kilogram square. Mass of the earth m is equal to 6 into 10 to the power 24 kg. And radius of the earth r is equal to 6.4 into 10 to the power 6 m. G is equal to g m by r square 6.7 into 10 to the power minus 11 into 6 into 10 to the power 24 by 6.4 into 10 to the power 6 meters square. That is equal to 9.8 meters square. Motion of objects under the influence of gravitational force on earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. Take a sheet of paper and a stone. Drop them simultaneously from the first floor of the building. Observe whether both of them reaches the ground simultaneously. We see the paper reaches the ground little later than the stone. This happens because of air resistance. The air offers resistance due to the friction of the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. We know that an object experiences acceleration during the free fall. This acceleration experienced by an object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As a g is constant near the earth, all the equations for the uniformly accelerated motion of objects become valid with the acceleration a replaced by g. This equation as v is equal to u plus at, s is equal to ut plus half at square, v square equal to u square plus 2as. For u and v are the initial and final velocities, x is the distance covered in time t. In applying these equations, we will take the acceleration a to be positive when it is in the direction of the velocity, that is, in the direction of motion. The acceleration a will be taken as negative when it opposes the motion. A car falls off a ledge and drop to the ground in 0.5 seconds. Let g is equal to 10 meter per second. What is the speed on tracking the ground and what is the average speed during 0.5 second? How high is the ledge from the ground? Time t is equal to half second. Initial velocity u is equal to 0 meter per second. Acceleration due to gravity g is equal to 10 meter per second. Acceleration of the car a equal to plus 10 meter per second. Speed v equal to 80. V equal to 10 meter per second into 0.5 second. 5 meter per second. Average speed equal to u plus v by tm. That's equal to 0 meter per second and 5 meter per second by 2.5 meter per second. Distance traveled is equal to half at square. Is half into 10 meter per second into 0.5 second whole square. Half into 10 meter per second into 0.25 square is equal to 1.25 meter. Its speed on striking the ground 5 meter per second. Average speed during the 0.5 second is equal to 2.5 meter per second. Height of the ledge from the ground 1.25 meter. An object is thrown vertically towards and rises to a height of 10 meter. Calculate the velocity with which the object was thrown upward and the time taken by the object to reach the highest point. Solution. Distance travelled is equal to 10 meter. Final velocity v is equal to 0 meter per second. Acceleration due to gravity 9.8 meter per second. Acceleration of the object a is equal to minus 9.8 meter per second. V square equal to u square plus 2as. 0 is equal to u square plus 2 into minus 9.8 meter per second into 10, that is minus u square is equal to minus 2 into 9.8 into 10 meter square seconds per second square. U is equal to root of 196 meter per second is equal to 14 meter per second. V equal to u plus 80, that is 0 is equal to 14 meter per second minus 9.8 meter per second into t. T is equal to 1.43 second. Initial velocity u equal to 14 meter per second and time equal to 1.43 seconds. Mass. We have learned in the previous chapter that the mass of an object is a measure of its inertia. We have also learned that greater the mass, greater is the inertia. It remains the same whether the object is on the earth, the moon, or even in outer space. Thus, the mass of an object is constant and does not change from place to place. Weight. We know that the earth attracts every object with a certain force, and the force depends on the mass of the object, acceleration due to gravity g. The weight of an object is the force with which it is attracted towards the earth. F is equal to m into a, that is F is equal to m into g. The force of attraction of the earth of an object is known as the weight of an object. It is denoted by W. Substituting the same in the equation, W is equal to m into g. The force of attraction of the earth on an object is known as the weight of the object. It is denoted by W. Substituting the same, W is equal to m into g. As the weight of an object is the force with which it is attracted towards the earth, SI unit of weight is same as that of the force. This is Newton. The weight is a force acting vertically downwards. It has both magnitude and direction. We have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to a mass. Say m of an object, that is W proportional to m. It is due to this reason that at a given place, we can use the weight of an object as a measure of its mass. The mass of an object remains the same everywhere, that is on the earth and on the planet, whereas its weight depends on the location because g depends on location. Weight of an object on the moon. We have learned that the weight of an object on the earth is the force with which the earth attracts object. In the same way, the weight of an object on the moon is the force with which the moon attracts the object. Mass of the moon is less than that of the earth. Due to this, the moon exerts lesser force of attraction on objects. Let the mass of an object be m and the weight of a moon be Wm. Let the mass of a moon be mm and radius is rm. By applying the universal law of gravitation, weight of an object on the moon will be Wm equal to g into mm into m by rm square. Let the weight of the same object on the earth be W, mass is m and the radius is r. Earth mass 5.98 into 10 to the power 24, radius 6.37 into 10 to the power 6. Moon 7.36 into 10 to the power 22, radius 1.74 into 10 to the power 6. From this equation, W is equal to G into m by r square. Substituting the values, we get W is equal to 2.431 into 10 to the power 10 G into m. W is equal to 1.474 into 10 to the power 11 G into m. Dividing this, we get 0.165 is equal to 1 by 6. Weight of the object on the moon 1 by weight of object on the earth 6, 1 by 6. Object on the moon is 1 by 6 into weight on the earth. Mass of an object is 10 kg, weight on the earth. Acceleration due to gravity, g is equal to 9.8 meter per second. W is equal to m into g. W equal to 10 kg into 9.8 meter per second. That is 98 Newton. Thus, weight of an object is 98 Newton. An object weighs 10 Newton when measured on the surface of the earth. What would be its weight when measured on the surface of the moon? Weight of object on the moon is 1 by 6 weight on the earth. That is Wm equal to W by 6, 10 by 6 Newton, 1.67 Newton. Weight of an object on the surface of the moon will be 1.67 N. Thrust and pressure. Have you ever wondered why a camel can run in a desert easily? Why an army tank weighing more than 1,000 ton rests upon a continuous chain? Why a truck or motor bus has much wider tires? Why cutting tools have sharp edges? In order to address these questions, understand the phenomena involved, it had to introduce the concepts of the net force of a particular direction and the force per unit area acting on the object concerned. Let us try to understand the meaning of the thrust and pressure by considering the following situation. Situation 1. You wish to fix a poster on the bulletin board as shown. To do this task, you will have to press drawing pins with your thumb. You apply force on the surface area of the head of the pin. The force is directed perpendicular to the surface of the board. This force acts on a small area at the tip of the pin. Solution. Situation 2. You stand on loose sand. Your feet go deep into the sand. Now lie down on the sand. You will find that our body will not be deep in the sand. In both the cases, force exerted on the sand is the weight of the body. You have learned that weight is the force acting vertically downwards. Here the force is acting perpendicular to the surface of the sand. The force acting on an object perpendicular to the surface is called thrust. When you stand on a loose sand, the force, that is weight of your body, is acting on an area equal to the area of your feet. When you lie down, the same force acts on an area equal to the contact area of the whole body, which is larger than the area of the feet. Thus, the effect of force on the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effect of thrust depends on the area where it acts. Effect of thrust on sand is larger while standing than while lying. The thrust on unit area is called pressure. Pressure equal to thrust by area. Substituting SI unit of thrust area, we get SI unit of pressure is Newton meter square. In hour of scientific place Pascal, the SI unit of pressure is called Pascal, denoted by PA. Let us consider a numerical example to understand the effect of thrust acting on different areas. A block of wood, it is kept on the tabletop. The mass of wooden block is 5 kg and a dimension of 40 cm into 20 into 10 cm. Find the pressure exerted. By the wooden block on the tabletop, it is made to lie in the tabletop with its sides of dimension 20 into 10 cm, 40 into 20 cm. The mass of the wooden block is 5 kg, dimension is 40 into 20 into 10. Here the weight of the wooden block applies a thrust on the tabletop. Thrust F is equal to M into G is equal to 49 Newton. Area of a side is equal to length into breadth is equal to 200 cm square is equal to 0.02 meter square. Pressure equal to 49 Newton by 0.02 meter square, 2450 Newton meter square. When the block lies on the sides of the dimension 40 into 20, it exerts the same thrust. Area equal to length into breadth is 40 into 20 is equal to 0.08 meter square. Pressure equal to 49 Newton by 0.08 meter square and is equal to 612.5 Newton meter square. Thus, the same force acting on a smaller area exerts a larger pressure and the smaller pressure on a larger area. This is the reason why a nail has a pointed tip, knives have sharp edges, and buildings have wide foundation. Pressure in fluids. All liquids are gas and fluids. A solid exerts pressure on its surface due to its weight. Similarly, fluids have weight and they also exert pressure on the base and walls of the container in which they are enclosed. Pressure exerted in any confirmed mass of fluid is transmitted and diminished in all directions. Buoyancy. Have you ever had a swim in a pool and felt lighter? Have you ever drawn water from a well and left the bucket of water heavier when it is out of water? Have you ever wondered why a ship made up of iron and steel do not sink in sea water, but while that of amount of iron and steel in the form of a sheet would sink? Question can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing this activity. Take an empty plastic bottle, close the mouth of the bottle with an airtight stopper. Put in a bucket filled with water. You see that the bottle floats. Push the bottle into water. You feel an upward push. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. Upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Now release the bottle, it bounces back to the surface. Does the force due to the gravitational attraction of the earth act on the bottle? If so, why doesn't the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction of the earth acts on the bottle in the downward direction. So the bottle is pulled downwards. But the water exerts an upward force on the bottle. Thus the bottle is pushed upwards. We have learned that weight of an object is a force due to the gravitational attraction of the earth. When the bottle is immersed, upward force exerted by the water on the bottle is greater than its weight. Therefore, it rises up when released. To keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by externally applied force acting downwards. This force must be at least be equal to the difference between the upward force and the weight of the bottle. Upward force exerted by the water on the bottle is known as upthrust or buoyancy force. In fact, all objects experience a force of buoyancy when they are immersed in a fluid. Magnitude of this buoyancy force depends on the density of the fluid. Why objects float or sink when placed on the surface of water? Let us do the following activities to arrive at the answer of the above question. Take a beaker filled with water. Take an iron nail or place it on the surface of the water. Observe what happens. The nail sinks. The force due to the gravitational attraction of the earth on the iron nail pulls it downwards. There is an upward thrust of water on the nail which pushes it upwards. But the downward force acting on the nail is greater than the upthrust of water on the nail. So it sinks. Take a beaker filled with water, take a piece of cork and an iron nail of equal mass. Place them on the surface of water. Observe what happens. The cork floats while the nail sinks. This happens because it's a difference in their densities. The density of a substance is defined as a mass per unit volume. Density of cork is less than the density of water. This means that the upthrust of water on the cork is greater than the weight of the cork, so it floats. Density of an iron nail is more than the density of water. This means that upthrust of water on the iron nail is less than the weight of the nail, so it sinks. Therefore, the object of density less than that of the liquid float on the liquid. Object of density greater than that the liquid sink in the liquid. Archimedes principle. Activity: take a piece of stone, tie it at one end of the rubber string or a spring balance. Suspend the stone by holding the balance of the string it is shown. Note the elongation of the string or the reading of the spring balance due to the weight of the stone. Now slowly dip the stone in the water or the container as shown in the figure. Observe the elongation of the rubber string due to the weight of the piece of a stone suspended from it in here. The elongation decreases as the stone is immersed in water. Observe what happens to elongation of the string or the reading of the balance. We will find the elongation of the string or the reading of the balance decreases as the stone is gradually lowered in the water. However, no further change is observed once the stone is yet fully immersed in the water. What do you infer from the decrease in the extensions of the string or the reading of the spring balance? We know that the elongation produced in the string or the spring balance is due to the weight of the stone. Since the extension decreases once the stone is lowered in water, it means that some force acts on the stone in upward direction. As a result, the net force on the string decreases and hence the elongation also decreases. As discussed earlier, this upward force exerted by water is known as the force of buoyancy. What is the magnitude of the buoyant force experienced by a body? Is it same all the fluids of a given body? Do all bodies of a given fluid experience the same buoyant force? Answer to the question is contained in Archimedes principle stated as follows. When a body is immersed fully or partially in a fluid, it experiences upward force that is equal to the weight of the fluid displaced by it. Now, can you explain why a further decrease in the elongation of a string was not observed in activity, as the stone was fully immersed in water? Archimedes was a Greek scientist. He discovered the principle subsequently named after him, after noticing that the water in a bathtub overflowed when he stepped into it. He ran through the streets shouting Eureka, which means I have got it. This knowledge helped him to determine the purity of the gold in the crown made for the king. His work in the field of geometry and mechanics made him famous. His understanding of levers, pulleys, wheels and axes helped the Greek army in its war with Roman army. Archimedes principle has many applications. It is used in designing ships and submarines. Lactometers, which are used to determine the purity of the sample of a milk, and hydrometer, used to determine density of liquids, are based on the principle. So that's all about this chapter. If you are interested, please do like, share and subscribe my channel. Okay, thank you.